In a carrier network, the number one requirement is uptime reliability. Customers have come to expect an SLA with at least 5 nines or 99.99% uptime. To maintain this level of service, the service provider cannot be reactive. Instead, they must be proactive and set up high availability in their network so that failures, when they occur, are completely unnoticed by the customer. So how can we leverage SDN to automatically and silently recover from a network outage? And as a bonus, how can we use those same algorithms to find alternative roads out of a city after a terrorist attack? One of the downsides of living in a big city is that our transport systems are always under attack by aliens, while the Avengers are busy fighting the aliens. If we don't have a backup plan already in place to get out of the city, then we're in big trouble. Let's take a look at this map of the London Underground. We start at South Kensington Station and we need to reach our destination, Russell Station. Obviously, the blue line is the most direct route, but what if there's an incident in Covent Garden? Then we'll need to find out the fastest alternative route, or multiple routes in fact, since who knows where the aliens will attack next. We'll see how mathematics can solve this problem and how networking can learn from it. The idea is simple, but in order to achieve such a result, there are several things we have to consider. To program a particular route onto network devices, traditional algorithms where each router has its own routing table will not work. The network devices should be controlled by a controller. This is where the SDN comes in, and technology like segment routing traffic engineering, or SRTE for short, can be used by the controller to engineer traffic flows in any way we want. Secondly, most routing algorithms are only interested in finding a single shortest path. To create a backup path for failover purposes, we need an algorithm that can find more than one path. So we need to consider not just the first shortest paths and so on, but the second, the third. Why stop at one backup path when you can have many backups? Lastly, just finding a lot of paths is not good enough. What if the paths are very similar to each other? Then a single failure will knock out the primary path and all the backup paths, and then we are back to square one. Thankfully, this problem has a name. Introduced in 2015 by researchers from Italy and Germany, it is known as the K shortest paths with limited overlap problem. Conveniently, they have also introduced an algorithm called OnePass that solves this problem. The OnePass algorithm introduces a similarity threshold known as theta that must be set by the network provider beforehand. For example, if the theta is 0.2, then each path cannot share more than 20% of the links. By setting a low value of theta and a high enough number of backup paths, we can ensure that no single link failure will break all the paths, thus achieving our high availability requirement. In fact, this problem also has applications for road networks as well as data networks. If a terrorist attack destroys many major roads, we can use the same algorithm to calculate alternative paths for vehicles to get from one place to another. So with the OnePass algorithm, we are now able to calculate multiple backup paths for each individual customer's connections. All that is left to do now is to have the SDN controller program these paths into the individual devices with a traffic engineering technology such as SRTE. If you liked this video, please hit the subscribe button, and for more information, check out our website in the link below.